Hello everyone, this is our third lecture covering Chapter 2. This lecture talks about chemical bonds. Before you get started, you're going to want to print out the study goals for Lecture Test 1 and keep it by you while you go through this lecture. You're also going to want to have a copy of the periodic table. You can get a copy of the periodic table from the course website in Module 2 or at the end of your textbook on appendix page 5. All right, so the other thing that you're going to want to do is you're going to make sure that you watch lecture 2 on the properties of atoms before you start this lecture. So we ended the previous lecture by defining a chemical bond, and we said a chemical bond is the force that holds two atoms together into a compound. And the ability to form chemical bonds is determined mainly by the number and the position of the electrons in an atom. To understand how the different types of chemical bonds form, we need to know a little bit more about where the electrons are and aren't within an atom. So this is a topic where you're just going to have to take my word for it. To really understand why this is true is really, it's a topic for an upper level physics or chemistry class. I barely understood it when I took this in college, and I certainly couldn't explain it now. So we're just going to take our word for it, but we need to know a little bit about where the electrons are. So electrons that are orbiting around the nucleus, and remember the electrons are moving really, really fast compared to the protons and the neutrons. The electrons are running around the nucleus and they have energy. And it makes sense that the farther away the electrons are from the nucleus, they have more energy. So imagine, I don't know if any of you have children, but imagine you're sitting with your friend at a picnic, talking to your friend, and you and your friend are sitting still, and meanwhile your children are running around, circling around the picnic, and the further away the children are from the picnic, usually the faster they're running. Okay. Well, so the electrons are orbiting around the nucleus and they have energy, and our first rule that we'll just have to take the physicist's word for it, is that the electrons are allowed only at specific energies. So or you can think about it as electrons are allowed only at specific places or distances from the nucleus. They're not allowed to be anywhere. So these energy levels that are allowed are called electron energy levels or electron shells. And the electron energy levels correlate with the distance from the nucleus. So the higher energy a level has, the further away it is from the nucleus. So the second thing that you're just going to have to take as given, as each energy level can only hold up to a certain number of electrons. It can have less than that number, but it can't have more than that number. The first energy level is the one that's closest into the nucleus, so it has the lowest energy. And the first energy level can hold at most 2 electrons. It can have less than 2, it just can't have more than 2. The second energy level out can have at most 8 electrons. The third energy level can also have at most 8 electrons, and we're not going to worry about filling up the fourth or the fifth energy levels. In biology, we're dealing mainly with the first, second, and third energy levels in our atoms. So again, the electrons are only allowed to be at specific certain distances. They're not allowed to be at other ones. And the ones that are allowed are called electron energy levels or electron shells. So let's look at some examples so you understand how this works. Each atom is going to have its own pattern of electrons, and we're going to assume for now that the number of electrons in an atom is equal to the number of protons. And the electrons are going to fill up the energy levels from the lowest out. So let's fill up the energy levels of a hydrogen atom. A hydrogen atom has 1 proton, so we're going to add 1 electron, and we're going to put that 1 electron in the first energy level. Remember, the first energy level can have up to 2 electrons, so that means that first energy level has 1 empty space that's waiting to be filled with an electron. Let's do another example. Let's do carbon. Carbon has 6 protons. You know that from the periodic table. So we're going to fill up the energy levels with 6 electrons. We're going to draw the first energy level and put 2 electrons in the first energy level, and now that energy level is full. So we're going to take the other 4 electrons and put them in the second energy level. So now we have 4 electrons in the second energy level, and we have 4 empty spaces that could be filled up. Let's do another one over here. Let's do oxygen, which has 8 protons. We're going to fill up the energy levels with 8 electrons. We put 2 electrons in the first energy level, and we put 6 electrons in the second energy level. That leaves 2 empty spaces to be filled up. I want to do another example just so you guys get the idea. And we're going to draw an atom really quick and fill up the energy levels. Now I'm going to put the nucleus here in the center, and I'm not going to draw in the protons and the neutrons in the nucleus, but that black ball is the nucleus. Now we're going to think about the electron energy levels. And so let's put the first energy level up there. And the example that I want to do is sodium. Now an atom of sodium has 11 protons. So we're going to fill it up with 11 electrons. And for an electron, I'm going to draw little circles like that. So we need to fill up the energy levels in the sodium atom with 11 electrons. So I'm going to put 2 electrons in the first energy level, and now that first energy level is filled up, so we need to move to the second energy level. I'm going to start filling up the second energy level. So I've got 1, 2, 3, 4, 5, 6, 7, 8 electrons in the second energy level, and now the second energy level is full. So I still have 1 more electron to go, so we're going to have to go out to the third energy level to put that last electron. So now we're going to put that last electron in the third energy level, and we're done. We've got 11 electrons, and I'll leave it to you guys. You can pause the lecture and count and make sure we got 11 electrons. So that means there's 2 electrons in the first level, 8 in the second level, and 1 electron in the third energy level. And that means that there's 7 empty spaces in that third energy level that need to be filled up. Now that we've practiced filling up the electrons in the energy levels, we want to talk about why it's important. So we want to define the valence shell. The valence shell is the outermost energy level that has electrons in it. And the electrons that are in that outer level are called the valence electrons. So let's go back and practice a little bit. Okay. So with hydrogen, The valence shell for hydrogen is the first shell, because that's the only one with electrons in it. And there's one electron in the valence shell for hydrogen. For carbon, the valence shell is the second shell, because that's the outermost. And there's 4 valence electrons in the valence shell with carbon. For oxygen, the valence shell is the second shell, and oxygen has 1, 2, 3, 4, 5, 6 valence electrons in it. And then to go back to our diagram of sodium that we drew before, sodium, the valence shell in an atom of sodium is the third shell, and sodium has 1 electron in its valence shell, or sometimes we'll say sodium has 1 valence electron. Why do we care about the number of electrons in the valence shell? That's what's going to determine the type and the number of chemical bonds that an atom can form. So we need to pay attention to how many valence electrons an atom has in its outer shell. And that's something I'm going to ask you to do on the test, and there are 2 ways to do it. The way that takes a lot of time is what we've just done. Draw a diagram of the atom, fill up the energy levels with the electrons from lowest to highest, and then look and see where the valence shell is and how many electrons it has in the valence shell. That's what we've just been doing in our examples. There's another way to tell how many valence electrons an atom has, and that's to use the periodic table. So let's talk about how that works. And you're going to want to go over this and over this and over this. So notice how the periodic table has the elements arranged in this really weird way, instead of just listing them all across. See how it has rows here, and it has columns here. Look at how many elements are in the first row. You've got hydrogen with 1 proton all the way over here, and helium with 2 protons all the way over here. Let's think about what the valence shells look like in both of those. Hydrogen has 1 proton and 1 electron in the valence shell. Helium has 2 protons and 2 electrons in that first valence shell. So helium, the valence shell is the first shell, and it's full. Remember, the first shell can't have more than 2 electrons. So as we go across a row of the periodic table, we're filling up a valence shell. So we have hydrogen and helium in the first row. We're filling up the first valence shell. When we want to jump to lithium, which has 3 protons and 3 electrons, we need to put 1 of those electrons in the second valence shell. So with lithium, let's take our lithium atom and mentally fill up the energy levels with 3 electrons. So you put 2 electrons in the first valence shell, and then you have 1 electron that you have to put in the second valence shell. Notice how lithium starts off the second row of the periodic table. As we're going to go across the second row, we're going to fill up that second valence shell with electrons. So lithium has 1 electron in the second valence shell. Beryllium here has 2 electrons in the second valence shell. Boron has 3. Carbon has 4 electrons in the second valence shell. Nitrogen has 5. Oxygen has 6. Fluorine has 7 electrons in the valence shell. When you get all the way over here to neon, you have 8 electrons in the second valence shell, and that means the second valence shell is full up. If we need to add more electrons, we need to jump up to the third valence shell, and those elements are indicated on the third row of the periodic table. So sodium has 1 electron in the one electron in the third valence shell. So it's the first element in the third row. Magnesium is going to have 2 electrons in the second valence shell. And we go all the way over here. Chlorine is going to have 7 electrons in the second valence shell. And we get over here to argon that has 8 electrons chlorine has 7 electrons in the third valence shell. And when we get over here all the way to argon, that's going to have 8 electrons in the third valence shell. And that means that third valence shell is full up. If we need to add more electrons, we got to jump down here to the fourth row where we're filling up the fourth valence shell. So potassium over here, we put 1 electron in that fourth valence shell. So we're working on the fourth row. So let's see what we can read out of the periodic table. Let's look at it, instead of looking at rows, let's look at columns over here. So all of these over on the left in this first column are all elements where we're starting to fill up a new valence shell. So that's telling you that all of these atoms here in this column all have 1 electron in the valence shell or outer shell. All of these atoms here have 2 electrons in the outer shell or valence shell. Now let's jump over to the end here. All of these at the end have different numbers of electrons in the valence shell. What you can say they all have in common, though, is their valence shell is always full up. So these all have a full valence shell. And the ones in column 17 over here, like fluorine and chlorine, are all just lacking 1 to be filled up. They're almost full, but not quite. So that means that all of the elements here are going to behave chemically very similar. They're all going to make similar covalent, they're all going to make chemical bonds in similar ways. Likewise, everything in the second column is going to make chemical bonds the same way. So let's learn about the relationship between the electrons in the valence shell and the chemical bonds. Well, atoms that have filled valence shells are stable. They don't react easily with other atoms, so they're not going to form chemical bonds. Atoms with unfilled valence shells form chemical bonds with other atoms in order to fill up those valence shells. So atoms just do not like to have unfilled shells, so they're going to try and make bonds to fill up the shells. And there are 2 types of chemical bonds that hold atoms together into compounds. The strongest type of bond is a covalent bond. And in a covalent bond, 2 atoms are actually sharing valence electrons. They're passing those electrons back and forth and sharing, and that makes a very strong bond between 2 atoms. With an ionic bond, atoms gain or lose electrons to become positively and negatively charged, and then attraction between the positive and negative charges holds the atoms together. I'm going to go in reverse order of the textbook because I want to talk about covalent bonds first. So in a covalent bond, atoms are sharing pairs of electrons. They're not sharing 1 electron, they're sharing 2 electrons. And with a single covalent bond, 1 pair of electrons is shared. So I want to, as an example of how covalent bonds are formed, I want to form a molecule of water. So a molecule of water has an atom of oxygen and 2 atoms of hydrogen. And let's make sure we understand about the valence electrons in the oxygen and the hydrogen before we form our bonds. So oxygen, 8 protons, we're going to fill the oxygen up with 8 electrons. 2 electrons go in the first shell. 6 electrons go in the outer shell or valence shell. So oxygen has 6 electrons in its outer shell. that means it has 2 empty spaces that need to be filled up. Remember, the second shell needs 8 electrons. So it's got 2 empty spaces to be filled up. Hydrogen has 1 electron that we're going to put in the first shell. So that means a hydrogen atom has 1 empty space in its first shell that needs to be filled up. So to form a covalent bond, one of the electrons from the oxygen and the electron from the hydrogen gets shared between the oxygen and the hydrogen. It's like this one comes down here and fills up the empty space here. I'm sorry about that. This one comes down and fills up the empty space in the oxygen. This one goes up and fills up the empty space in the hydrogen. And the hydrogen and the oxygen atom share that pair of electrons. And you can see that happening here. One of the electrons in the pair came from the hydrogen, one came from the oxygen, and they're going to share. That's what we call a single covalent bond. So it takes 2 electrons shared to make a single covalent bond. And then the other hydrogen atom is going to come over here and share and form a second single covalent bond there. Now, what does it mean when the electrons are shared? Well, remember, electrons are orbiting really, really fast around the nuclei of the atom. The hydrogen electrons orbiting around here, the oxygen atoms orbiting around here. So what happens to those electrons when they share? Well, it's like they get passed back and forth between the 2 nuclei. So this electron is going to spend some time orbiting around the oxygen nucleus, but it's also going to spend some time orbiting around the hydrogen. It's going to get, that electron is going to get passed back and forth between the 2 atoms. Same thing is going to happen over here. This electron is going to spend some time around the hydrogen, orbit around the oxygen, go back to the hydrogen. So it's essentially going to get passed back and forth between the oxygen atom and the hydrogen atom. And that's how a covalent bond forms. My favorite analogy for a covalent bond is to imagine 2 people that are juggling. Have you ever seen 2 people that are juggling balls that pass the balls back and forth between them? If they're doing that and one person starts to move off, the other person has to follow in order to keep those balls in the air. So passing the balls back and forth is kind of the way that the electrons get passed back and forth between the atoms in a single covalent bond. So if a single covalent bond is sharing 2 electrons, in a double covalent bond, 2 atoms are sharing 4 electrons. Here's an example of a compound called carbon dioxide that you've probably heard of. The carbon atom in the middle makes a double covalent bond with 1 oxygen atom over here and a double covalent bond with another oxygen atom over here. So here are the 4 electrons being shared in the double covalent bond. And 2 of those electrons come from the oxygen atom, 2 of those electrons come from the carbon atom. Now there are triple covalent bonds. In biology, the compounds that have triple covalent bonds are mostly toxic, so we're going to stick with single and double covalent bonds. We want to do a little sidebar here and talk about some notation that you're going to see. So we've learned already about chemical formulas. Chemical formula shows all the atoms that are present in a compound and tells you how many there are. So this is the chemical formula for methane. And this is telling you that methane has 1 atom of carbon and 4 atoms of hydrogen. The chemical formula doesn't tell you anything about what types of chemical bonds are there or where they are. To indicate covalent bonds and the location of covalent bonds in a molecule, we use something called the structural formula. And the structural formula shows the location of the atoms, and it also shows the location of the covalent bonds. So this is the structural formula for methane, and it's showing you that the carbon atom is in the middle, and that each hydrogen atom in methane makes a single covalent bond with the carbon. A single line indicates a single covalent bond. So the two types of notation we're going to use most often are the chemical formulas and the structural formulas. Occasionally, if we want to show you something about the three-dimensional shape of a molecule, we will use something called a space-filling model. And a space-filling model, it's kind of like you build the molecule or the compound with little balls of Play-Doh, and each little ball is a different atom. So here you see the space-filling model for methane. It's got the single carbon atom in the middle and 1, 2, 3, 4 hydrogen atoms around it. And now you can see that methane isn't flat like a pancake the way it looks in the structural formula. It's actually more like a pyramid. I want to stop and define a term that we've been using without defining it. A molecule is a compound in which the atoms are held together by covalent bonds. So when people use the term molecule, they specifically are talking about covalent bonds. Now, let's look at some examples. Don't get nervous. Sometimes people get nervous when we start talking about chemical formulas and structural formulas because they think that they're going to have to memorize all these. You won't. The only chemical formula and structural formula that you have to memorize is water. H2O for the chemical formula, and the structural formula looks like this. It's important that water has that bend in it. The hydrogens don't stick out on either side of the water like this. It actually has an angle in it. That's going to be important for some of the properties of water that we're going to talk about later. So here's an example of some other molecules that exist in your body. Here's a molecule of hydrogen. It's got two atoms of hydrogen with a single covalent bond between them. And most of the hydrogen that's in the atmosphere that we breathe is present as hydrogen molecule rather than single hydrogen atoms. Here's an example of a molecule of oxygen. It's got two atoms of oxygen with a double covalent bond in it. There are two lines as a double covalent bond. Most of the oxygen in the atmosphere is actually present as molecular oxygen with a double covalent bond, not as free oxygen atoms. Don't panic, I just wanted to show you some more complicated structural and space-filling formulas. We're going to look at these in more detail in the last lecture on organic molecules. This is the structural formula of a molecule of glucose, which is blood sugar. And just ignore that purple color in the middle, that doesn't mean anything. This is telling you that the carbon and the oxygen atoms in the glucose, the covalent bonds put them together to form this ring structure. Okay. Here's another example. This is a molecule of lauric acid, which is something called a fatty acid. That's part of the fats in our body. And again, you can see the structural formula. And while it's very complicated, if you break it down and take it one part at a time, you can interpret it. So a C is just an atom of carbon. An O is an atom of oxygen. A single line is a single covalent bond, and a double line is a double covalent bond. Now on the test, I might give you a structural formula like this. I don't expect you to know that that's lauric acid, but I do expect you to look at the parts. And so for example, if I asked you what the C meant, you would say an atom of carbon. If I asked you what a single line meant, you would tell me, oh, that's a single covalent bond. So that's the kind of question I'm going to be asking you on the test. All right, I want to define something now called a polar covalent bond. And you're just going to take this idea for now and park it in the back of your head. It's going to become important in a minute. Remember we said that in a covalent bond, two atoms are sharing electrons by passing them back and forth. If they're passing them back and forth, though, that they're sharing them equally. In other words, an electron spends as much time around this hydrogen atom as it does around the oxygen atom, then we say that's a non-polar covalent bond. Remember, polarized means things sort of shift to one side. And with non-polar, it means that the electrons are being shared evenly and fairly. So that means the electrons spend as much time over the hydrogen as they do over the oxygen. Some covalent bonds are like that. In other types of covalent bonds, though, the two atoms share the electrons unequally. So water contains two, and that's called a polar covalent bond. Water contains two polar covalent bonds. In water, the electrons spend more time orbiting around the oxygen atom than they do orbiting around the hydrogen atom. So the electrons might go 5 times around here and once around here, and 5 times around here, once around here. So if the electrons are shifted towards one atom, that's a polar covalent bond. This is a slide that you need to memorize. This isn't in the textbook, but we're going to use this idea later on when we get to the last lecture. You need to memorize, you don't need to memorize every polar and nonpolar covalent bond, but you do need to memorize these. So if both atoms are the same, it doesn't matter if it's a single or double covalent bond. If both atoms are the same, they're going to share the electrons equally. So these are going to be nonpolar covalent bonds. Also, if you have a carbon covalently bonded to a hydrogen atom, that's going to be a nonpolar covalent bond. These are going to be polar, so carbon to oxygen, carbon to nitrogen, hydrogen to oxygen, or hydrogen to nitrogen. All of these, the electrons are going to spend more time around the oxygen or more time around the nitrogen than they do around the other atoms. So these are all going to be polar covalent bonds. And again, this is just something you need to memorize. We'll talk about why it's important later on. Okay. I want to switch now and talk about an ionic bond. So an ionic bond forms when one atom just completely gives up an electron, another atom takes the electron, and then the atoms are held together not by sharing those electrons, but by attraction between a positive and a negative charge. So here we have an atom of sodium, and sodium, what we've learned so far is that sodium has 11 positive protons and 11 electrons. Now that sodium atom, because it only has one electron in that outer shell, is just going to give away that electron. And now, now it has less electrons than it does protons, so it's going to become positively charged. In other words, more protons, more positive protons than negative electrons, it's going to become positively charged. If it gets close to a chlorine atom, it's just going to give that electron away to the chlorine atom. Remember, chlorine atom has 7 electrons in its outer shell. It's only missing 1 to have a full outer shell. So the chlorine is just going to take that extra electron, and now the chlorine has 1 more electrons than it does protons. So chlorine is going to become negatively charged. Now, the sodium giving the electron to the chlorine is not what forms the ionic bond. Now, because the sodium is positive and the chlorine is negative, it's the attraction between the positive sodium and the negative chlorine that forms that ionic bond. So atoms become ions by losing or gaining electrons in the valence shell, and then once they've lost or gained the electron, if you get a positive ion near a negative ion, they're going to stick together by the charge attraction. And this is just an aside, compounds that are held together by ionic bonds are often called salts. And they're crystals in the solid state. And compounds that are held together by ionic bonds are generally going to separate into the ions when you dissolve them in water. Covalent bonds are stronger than ionic bonds, and they're generally not going to separate in water, but ionic bonds often are. We'll talk a little bit how that works later. Okay, I want you guys to be able to use the periodic table to predict the type of chemical bond that an atom will make. So all of the atoms in column 1, remember all the atoms in column 1 only have one valence electron in that outer shell. The easiest thing for them to get a full outer shell is just to give away that one electron and drop down to the lowest shell lower there. So the atoms in column 1 are all going to give away one electron. And when they give away an electron, they're going to become cations with a charge of +1 because they've given away an electron. They've given away an electron, so now they have more protons than electrons. They're going to have a charge of +1. The atoms in column 2 also only have 2 electrons in the valence shell. The easiest thing for them to do is to give those electrons away. So the atoms in column 2 are going to become cations with a charge of +2. The atoms in column 17, fluorine and chlorine, those are only need 1 electron to have a full outer shell. So these are the atoms that are going to take an electron from the ones in 1 and 2. These are going to take an electron, so they're going to have an extra electron compared to new protons, so they're going to become anions with a charge of -1. So atoms in column 1 are going to have a charge of +1. Atoms in column 2 are going to have a charge of +2. Atoms in column 17 are going to have a charge of -1. So if you get an atom with a positive charge close to an atom with a negative charge, they're going to stick together and form an ionic bond. So when you're going to learn in chemistry class, it's more complicated than this. But for biology class, atoms in column 1 and 2 are going to become cations. Atoms in column 17 are going to become anions. And then the atoms sort of up in the upper right corner, carbon, oxygen, nitrogen, phosphorus, and sulfur, are going to form covalent bonds. Okay, I call that covalent corner of the periodic table. Meanwhile, hydrogen is a little tricky because hydrogen only has 1 electron. Hydrogen will form covalent bonds. Hydrogen will share, but it also, that proton in hydrogen separates out easily from the molecule. So frequently when you put something with, sometimes when you put something with hydrogen on it, it will jump off and separate when you dissolve it in water. When we talk about acids and bases, we'll talk about more about that. So I want you to be able to use the periodic table to predict whether a particular type of atom will form ionic bonds by becoming an ion or form covalent bonds. And to do that, you use the slide here. And during our Zoom classes, we will practice doing this a lot. Now, it's not just atoms that can become ions. Entire molecules can lose or gain electrons to become ions. So if you have an ionic molecule, that can form an ionic bond with other ions. So for example, we talked about, in a previous lecture, we talked about the phosphate ion. That's a molecule that has a phosphorus in the middle, 4 oxygen, and the phosphorus and the oxygen are all held together by covalent bonds, but that entire molecule has also gained 3 electrons, so it has a charge of -3. Here's our hydroxide ion. That's a molecule of oxygen and hydrogen held together with a single covalent bond, but that entire molecule has gained an extra electron to have a negative charge. Now, if I get a negative hydroxide ion, close to a positive sodium ion, they will form an ionic bond between the hydroxide and the sodium. All right, just so you know, you've probably heard a lot about free radicals and damaging your skin. If you watch late night cosmetics commercials, infomercials, a lot of times you'll hear about free radicals. A free radical is an atom or a molecule that has an unfilled valence shell. For example, a single atom of oxygen floating around is going to have 2 empty spaces that need to be filled up in its valence shell. Now, free radicals are very reactive. They go around trying to find electrons to pull off of other things in order to fill up that outer shell. So they'll pull electrons from anywhere they can find. So when they pull electrons out of molecules, such as proteins and DNA, they can damage those molecules. Okay. Here's an example of an oxygen atom that's a free radical. Here's an example of a compound or a molecule with a covalent bond. That covalent bond, that double covalent bond, still between an oxygen and nitrogen, still didn't manage to fill up the outer shell of the oxygen. So this compound called nitric oxide is still going to be very reactive until it gets a full outer shell. Covalent bonds and hydrogen bonds are the 2 types of bonds that hold 2 atoms together into compounds. However, there are several types of weak chemical bonds that can hold molecules together. And these weaker chemical bonds are important for holding larger molecules into the correct shape. And they're also important for helping molecules dissolve in water. We're going to talk about one type of weak chemical bond called the hydrogen bond. And a hydrogen bond is a weak force that holds 2 polar molecules together. So polar molecules are molecules that have one end that has a little bit of positive charge on it and another end that has a little bit of negative charge in it. So to form a hydrogen bond, a positively charged region of one molecule is attracted to a negatively charged region of another molecule. That's easier to understand with a diagram than with words. So we talked about polar covalent bonds. Polar covalent bonds are covalent bonds where electrons are shared unequally, and that means electrons spend more time over one atom in the molecule than they do over another one. So a molecule with some polar covalent bonds in it forms a polar molecule. So in a polar molecule, the electrons shift to one end of the molecule, or maybe more than one end of the molecule. So I've just sort of drawn a generic lumpy drawing of a polar molecule, because for now I don't really care what the different atoms are. What I care is that the electrons are spending more time orbiting around this end of the molecule than around this end. So the electrons have shifted more down to this end. That means that this end of the molecule has a little bit more negative charge because of those electrons spending more time there. Meanwhile, the electrons spend this less time down here. There's still protons down here. So this end of the molecule has a little bit more positive charge on it. So the electrons are uneven. That means this end of the molecule is a little bit negative charged. This end of the molecule is a little bit positive charged. Now this is important. Polar molecules are not ions. They have not gained or lost electrons overall, so the net charge is still 0. It's just the electrons have shifted to one side. The analogy that I like to use is, I imagine like going to the Home Depot to buy some bricks to build a garden at my home. So I load up the trunk of my car with the bricks, and when you first put them in the trunk of the car, you're going to try and load the bricks up evenly so the weight's not all on one side of the car. and then I close the trunk and I take off driving, and imagine I've got all those bricks in the back and you take a corner a little too fast. What's going to happen? Those bricks are all going to shift over to one side of the trunk, and that means there's going to be more weight on one side than on the other. Okay, notice I haven't lost or gained any bricks. They've just shifted to one side. That's what happens in a polar molecule. You don't lose or gain electrons to become an ion. They just shift to one end, but that gives that end a little more negative charge, and the opposite end is going to have a little more positive charge. Now, we haven't talked about hydrogen bonds yet. We've only talked about polar molecules. To make a hydrogen bond, you get the negative end of one polar molecule close to the positive end of another polar molecule, and there's an attraction between the negative charge and the positive charge. That's where the hydrogen bond is, between those two polar molecules. Let's look at a real example of a polar molecule, and then we'll look at a real example of a hydrogen bond. So water is a polar molecule. The covalent bond between hydrogen and oxygen is a polar covalent bond, and the electrons in water spend more time around the oxygen than they do around the hydrogens. That means that the oxygen side of the water molecule is going to be a little bit negative, and the hydrogen ends of the water are going to be a little bit positive. The same thing with ammonia. Ammonia is a nitrogen and 3 hydrogens. Hydrogen to nitrogen is a polar covalent bond. You're going to memorize that on the slide that I told you. And the electrons spend more time around the nitrogen than they do around the hydrogen. So this end of ammonia is going to be more negatively charged. What happens when you get the negative end of an ammonia molecule close to the positive end of a water molecule? Well, there's an attraction between the negative and the positive charge. That's the hydrogen bond in there. Okay. What about these here? Those are not hydrogen bonds. Those are polar covalent bonds within one molecule. Okay. So study this diagram carefully and make sure that you can recognize the difference between the polar covalent bonds and the hydrogen bonds. Okay. Hydrogen bonds we'll talk more about in the next section. Hydrogen bonds form between molecules in a glass of water. You can see a diagram here. The negative end of one water molecule is attracted to the positive end of another water molecule. So hydrogen bonds form a very important force that hold water molecules together. They're also responsible for helping other polar molecules dissolve in water. And hydrogen bonds are a very important force that holds DNA and proteins into the correct three-dimensional shape.